Hello, welcome to this video lesson for higher physics in the Our Dynamic Universe section, looking at gravitation and Newton's universal law of gravitation. What we're looking at today is how to describe the force acting between two masses as we change the distance between those two masses, the relationship for the universal law of gravitation, and example calculations using this relationship. So we will already be familiar with the differences between mass and weight, mass being the amount of matter in an object measured in kilograms, weight being the force due to gravity acting upon that mass. So a gravitational force is caused by any object with a mass, and all masses have their own gravitational field. But the size or magnitude of that gravitational field depends upon the mass of the object. And so we don't notice this in everyday existence apart from the gravitational fields between the Earth and ourselves, because the masses are relatively small and therefore the gravitational fields are small between other masses. Gravitational force is a vector quantity, and gravitational field is also a vector quantity. It's best not to use the word gravity, but to use either gravitational force or gravitational field or strength or gravitational acceleration, because if you just use the word gravity, it could apply to either of those two and therefore is ambiguous. So make sure you put gravitational force or weight if you're describing the force, or gravitational field strength if that's what property you're describing. So all masses create these gravitational forces, but they are so small that we don't notice them. What's normally the case is that the friction between objects is too great, so the objects don't move together because of the gravitational forces. The Earth has an enormous mass, 6 times 10 to the 24 kilograms, and yet the gravitational field strength even for that large mass is only 10 newtons per kilogram. Gravitational fields and gravitational forces act over an infinite range. So to escape the gravitational field, you have to get to infinity. If you go on and do advanced high physics, we'll do more about escape velocities. So Newton's universal law of gravitation says that the gravitational force is equal to a constant called big G, the universal constant of gravitation, times the product of the two masses, m1, the mass of the one object, and m2, the mass of the other object, divided by the distance between those objects, r squared. So the greater the masses, the greater the force. And the greater the separation, the less the force. But it's an inverse square law relationship because it's divided by r squared in a similar way to the irradiance function, which was k over d squared. Now we've already defined 1 Newton as being the force required to accelerate 1 kilogram of mass at 1 meters per second squared. So when you have two 1 kilogram masses placed 1 meter apart, you find that that is much less than 1 Newton. In fact, 6.67 times 10 to the minus 11 newtons, and therefore that is the value of the universal constant big G. So big G can be found on the relationship sheet, on the data sheet at the front of the exam paper with the other constants. So the further away you go from Earth, the less the force of gravity is. So far, when we're looking at gravitational fields at National 5, we've assumed that they're constant, whereas reality, they change with distance from the Earth. So the gravitational field strength at the top of Everest will be less than the gravitational field strength at sea level as a result of this. And the force of gravity decreases with the square of the distance from the center of the Earth. So if an apple weighs 1 Newton at 1 diameter from the Earth on the Earth's surface, at 2 diameters away, it will be 1 over 2 squared, 2 squared being 4, so it'll be a quarter of the force. If it's 3 diameters away, it'll be a 9th of the force. If it's 4 diameters away, it'll be a 16th of the force, etc. So you can see how it's rapidly decreasing. Okay, so sometimes you can make calculations using the gravitational force relationship. Sometimes you can make an estimation, because if you double the distance you are away from the Earth, then the force due to the Earth will be a quarter of what it would have been originally. Okay, the convention is to use r rather than d for the distance, because we're looking at a radius from any particular point. So it doesn't matter if you've gone 2 distances to the right or 2 distances to the left. They're the same distance from the center of the Earth. Okay, here's just a snapshot to show that you can find the universal constant of gravitation, big G, on the relationship sheet here. Okay, together with the gravitational acceleration on Earth. So let's have a look about what kind of values for these forces would be. So if we consider a folder that has a particular mass, 0.3 kilograms, 300 grams, and a pen that has a mass of 0.05 kilograms, that are 0.25, 25 centimeters apart, we can work out the magnitude of the gravitational force between the two masses. Both will be attracting each other. Now we've assumed in this that they're point masses, they're just circular and they're like that, whereas we know that both a folder and a pen would not be like that. So we can list our masses, M1 and an M2, and our separation, and big G, and we can substitute into our relationship G times M over R squared, and we can see that we get a force of 1.6 times 10 to the minus 11 newtons. Now that force is insufficient to overcome the friction, so it's not like you suddenly see the folder and the pen moving towards each other, because the frictional forces are much greater than the gravitational force. So gravitational forces are actually quite weak. They're less strong than all the other forces. So the electrostatic force between two charges is much greater, and equally the strong and the weak forces that act within the nuclei are much greater as well. Now, we should already know from National 5 that the gravitational field strength is the weight per unit mass, and we can get that from W equals mg by describing G as being equal to W divided by M. So it's equivalent to the force on a 1 kilogram mass placed within that gravitational field. So we can calculate G on the surface of the Earth given some information about the Earth, given its radius and given its mass. This information has to be given to you in the question at higher physics. Okay, so our example here is to calculate G, little g this time, so the gravitational field strength or the acceleration due to gravity. So since the weight is due to the gravitational force, m times g is equal to g times m over r squared. And we can cancel the mass of the object out of that relationship, and then the acceleration due to gravity is big G times the mass of the Earth divided by the radius of the Earth squared. And we end up using our figures there of 9.77 newtons per kilogram, which is where our value of 9.8 newtons per kilogram comes from on our data sheet. Okay, so we could do a similar exercise to look at the gravitational field strength on the moon based upon the mass of the moon and the radius of the moon. And again, the weight is equal to the gravitational force. We can cancel out the mass of the individual object because it doesn't matter what the mass of the object is. Light things and heavy things fall at the same rate. And then we can work out G on the moon to be 1.68 newtons per kilogram, or 1.68 meters per second squared, because gravitational field strength and acceleration due to gravity gravity are equivalent, so either unit would be acceptable in this case. Okay, we could also look at the force between the moon and the earth. So we know that the moon orbits the earth, and the moon orbits the earth, is a natural satellite of the earth because of the gravitational force between the two objects. And we can work out what that force of attraction between these two objects is by substituting into Newton's universal law of gravitation. So we've got big G times the mass of the earth multiplied by the mass of the moon, which is on the previous page, and divided by the mean radius of the moon's orbit around the earth. And we see that the force there is nearly 2 times 10 to the 20 newtons between the two. Okay, so let's have a look at a slightly different problem here. So we've got a question here that tells us there's a communication satellite orbiting the Earth at a height of 36.0 times 10 to the 6 meters above the surface of the Earth. And we're given the mass of the Earth, 6.0 times 10 to the 24, and the radius of the Earth, 6.4 times 10 to the 6. And the first part of the question asks us to determine the distance between the center of the Earth and the satellite. So you'll notice here that we're given the altitude or the height above the surface of the Earth of the satellite. So to get the distance to the center of the Earth, or the radius, we need to add those two values together. And we'll get 42.4 times 10 to the 6 meters. Okay. So for part B, we are asked to calculate the mass of the satellite. And we're told that the gravitational force of attraction between the Earth and the satellite is 57 newtons. So the best way to approach the question is to list out the things that we know. So we know the force, we know the mass of the Earth, we want the mass of the satellite, and we know from part A the radius, the height above the surface of the Earth plus the radius of the Earth. So we've got the distance there, and we know that we need big G, given that we're going to use Newton's universal law of gravitation, which F equals G times M over R squared. So we substitute into our values first, and then we rearrange our relationship. Now you can rearrange them with the values as written, or you could multiply out the top term and the bottom term, or you could divide all the top terms by the bottom terms to give a number times m equals 57. Okay, either way you end up with a value that of 256.1 kilograms. And given, if you look at all the data in the question, we've got 36.0, 3 significant figures, or we've got 6.4, 2 significant figures as the least numbers. So 260 is actually the correct number of significant figures, which is 2, but you could put 3 significant figures, or you could get away with 4 significant figures as well. Okay, we're then asked to determine the value of the Earth's gravitational field strength at the satellite. So we know that the gravitational field strength and the gravitational force decrease with the distance from the Earth, and so we want to work out exactly what that happens to be. So the one approach we can have is we can say, well, the force at that point is equal to the weight, which is equal to m times g. So if we take our 57 newtons that we had in the previous question and our mass that we worked out from the previous question, we can divide those two to get 0.22 newtons per kilogram. An alternative approach would be to say the gravitational force is equal to the weight. So we've got mg equals g times m over r squared. The mass of the satellite cancels, and we can then substitute the details about the Earth and the distance from the satellite to the Earth, and we end up with the same value. So either of these approaches would give you maximum marks here because they're both identical. Okay, the final part of the question gives us a different situation. So it says the second satellite has a quarter of the mass of the first satellite. The distance from the center of the Earth to the second satellite is half the distance it was in the first situation. State how the gravitational force of attraction between the second satellite and the Earth compares to the gravitational force of attraction between the first satellite and the Earth. And we have to justify our answer. Okay, so it's got quarter of the mass and it's half as far away as the first situation. So you've got two approaches here. You can describe and justify using the relationship, or you can make a calculation with some actual numbers and then describe what that means. And I'll show you both of these here. So if we look at what the relationship is, because F equals G times M over R squared. So if we have a quarter of the mass, then the top line is a quarter of what it is before. So it's quarters the force. If the orbital height is halved, then that's going to have the effect of dividing by a half squared, which means we're going to get 4 times the amount of force. So the consequence of that is that the overall force is the same. So you would probably want to write these statements also writing the relationship too. The alternative is you could make some calculations and you could say, well, I knew the first time that the mass of the satellite was 256. If I divide that by 4, that is 64 kilograms. Okay, do be careful, because if you've rounded your answer earlier to 260 kilograms, that wasn't wrong for the earlier answer, but it will mean that you might get a slightly different answer here if you take that original value there. So 64 kilograms, and then we're looking at halving the distance. So it was 42.4, and we've halved it to 21.2. So you can substitute in those numbers, G times the mass of the Earth times 65 divided by the half the distance squared, and you end up with 57 newtons. So the force is the same. So like I say, you would have to be a little bit careful if you rounded the mass of the satellite earlier, or indeed the distance. We didn't in this case, but it's possible that we might have done. Then you may get a number that is not exactly the same. Whereas the force will be exactly the same, because one has got a quarter more and one has got a quarter less. So these two factors cancel out. Okay, so what we looked at in this video is we looked at how to describe the force acting between two masses, and we've looked at the Newton's law of gravitation and how to make calculations using this of the gravitational force or the gravitational field strength.